You know it. It's probably the most famous equation in all of history. E equals mc². It's on mugs, it's on t-shirts, it's basically the symbol for genius. But what if I told you that the equation you think you know isn't really the full story? Today, we're going to deconstruct it and find out what it really means.
And there is no doubt about how important it is. Einstein himself called this idea, the equivalence of mass and energy, the most important upshot of his whole special theory of relativity. This wasn't just some little footnote for him. He saw it as a central pillar, a brand new principle of physics that was going to change how we saw the entire universe.
Okay, so here's where we get to our first big surprise. See the equation on the left? That's the one everybody knows. But it's a simplified version and it can be a bit misleading. The one on the right, with that little subscript O, that's what Einstein was actually talking about. That tiny symbol, it stands for rest, and it changes absolutely everything. Understanding that is the key to this whole thing.
All right, so let's rewind. Let's go all the way back to Einstein's revolutionary paper from 1905 and see what he actually said. This right here was the bombshell. He didn't start with E equals mc². He first argued that if a body gives off or takes in energy like a flash of light, its mass actually changes. I mean, this was totally radical. In the old-school Newtonian world, an object's mass was fixed. It was constant. And Einstein comes along and says, no, you can change an object's mass just by shining a light on it.
So then, what does Einstein's real equation, E0 equals c² actually mean? Let's break it down. Before Einstein, this was basically the law of the land in physics. An object's inertial mass was just its built-in resistance to being pushed around. It was this fundamental, unchanging property. If you wanted to change an object's mass, you had to literally chop a piece off or glue a piece on. It was static.
So what did Einstein figure out that just completely turned this idea on its head? What he discovered was that an object's rest mass, the m in this equation, is actually a measure of the total energy it has packed inside of it, even when it's sitting perfectly still. That's the rest energy, the E0. And the crucial thing is that rest mass, m, is an invariant quantity. It's the same for everybody, no matter how they're moving. So mass wasn't just about resisting motion anymore. It was a giant reservoir of energy.
And this makes the whole concept surprisingly down to earth. When you heat up a brick, you're adding energy to it, and so you are literally, physically, increasing its mass. Same thing when you charge a battery. A container of hot gas is actually more massive than that same container with cold gas, because all the kinetic energy of those zipping gas molecules adds to the total mass of the system. So how much mass are we talking about here? I mean, is it a lot? Well, the effect is unbelievably tiny in our everyday world. Imagine the energy it would take to get a battery moving at 670 miles per hour. Now, what if you took that same amount of energy and used it to charge the battery instead? Its mass would only increase by 1/trillionth. It's an incredibly small change, but it's real. It's there. And this leads to a really profound consequence. Energy itself has inertia. And because gravity is linked to inertia, energy also has weight. So if you had a box with perfectly mirrored walls and you filled it with light, just trapped photons bouncing around, that box would actually weigh more than an identical empty one. The energy of that trapped light adds to the system's total mass. Now, this effect might be minuscule for a battery, but it gets seriously dramatic when you go down to the atomic level, where the energies involved are just enormous. The first real proof came in 1932. Scientists smashed a proton into a lithium atom, and what they found was amazing. The particles that came flying out at the end had less total mass than the particles that went in. This missing mass hadn't just vanished into thin air. It had been released as a huge blast of kinetic energy. And the amount of energy was exactly what Einstein's equation predicted it would.
So here's a really crucial point, and it's a common misunderstanding. Most physicists today wouldn't say that mass was converted into energy here. That's not quite right. See, the energy was there the whole time, locked away as potential energy inside the nucleus. The reaction just unlocked it. It transformed that potential energy into the kinetic energy of the particles flying away.
And that decrease in potential energy shows up on the scales as a decrease in the system's total rest mass. But okay, what about the most extreme case you can imagine? Pair annihilation. You take an electron and its antimatter twin, a positron. They both have rest mass, they collide, and poof, they annihilate each other. What's left are two photons, particles of light that have zero rest mass. It really, really looks like mass just disappeared and turned into pure energy.
But, and this is the subtle, kind of mind-bending part, even though those individual photons have no rest mass on their own, the system of the two photons flying away from each other does have a rest mass. The total mass and the total energy of the entire system, before, during, and after, is conserved. The stuff didn't actually vanish. It was just rearranged into a new form that carries all the properties of the original system.
As you can probably guess, these ideas kicked off some pretty intense philosophical arguments that are still going on today. I mean, what does it really mean for mass and energy to be equivalent?
The whole debate really falls into a few different camps. You've got some who say, look, mass and energy are just two different ways of measuring the exact same thing, like using inches instead of centimeters. Others say, no, they're fundamentally different properties, and there's no conversion happening, just transformation. And then there's a third group that says they're different, but a genuine conversion from one to the other is possible in some cases.
Ultimately, the debate just boils down to this question. When we see mass go down and energy go up, is that a real physical process where one thing is literally turning into another? Or are we just changing how we do the accounting, shifting our focus from the little pieces inside to the properties of the system as a whole? And this philosophical puzzle leads us to an even deeper, more fundamental question about the very nature of reality itself. If mass and energy are so deeply connected, then what is the fundamental stuff of the universe actually made of?
Well, Einstein and his collaborator Leopold Infeld argued that this equation totally collapses one of the main pillars of classical physics. We used to have these nice, neat boxes. You had matter, which has mass, over here, and you had fields, which carry energy over there. But if mass is just a form of energy, you can't really make that distinction anymore. The line between them just gets incredibly fuzzy.
Einstein put it pretty simply back in 1907. He described mass as being equivalent to an energy content. This idea suggests that what we perceive as solid, tangible matter is, at its very core, just a tremendously concentrated form of energy, all bound up and contained inside a particle.
And that leaves us with this final, profound question to think about. If all the mass in the universe, the chair you're on, the planet you're on, your own body, is ultimately just a form of contained, concentrated energy, what does that make the world? It suggests that the solid, stable reality we experience every day is really just one manifestation of a much more fundamental, dynamic, and energetic universe.